Good morning. So we are starting with consumer theory. I recall what we did at the end of the last session. We assume that the consumer has preferences represented by a total pre-order on R plus N, R plus N is the set of commodity bundles, and this total pre-order means that X is related to Y, means that the commodity bundle X is preferred to the commodity bundle Y, that they are indifferent. Okay? And I mentioned that to work with total pre-orders in abstract is difficult, so it's good when we have a so-called utility representation. So we say that U from R plus N into R is a utility function, a utility representation of the pre-order if the following equivalence holds true. X preferred to Y if and only if U of X is greater than or equal to Y. So if such a utility representation is available, comparing two commodity bundles, which are two vectors, reduces to comparing two numbers, two real numbers. If we want to find our most preferred commodity bundles, we just have to maximize the utility function. And we are familiar with maximization of functions, okay? And I presented a theorem due to Gerard Debreu, which says that such a utility representation exists and is continuous if and only if the total pre-order is continuous, which means that its graph is a closed set. Its graph being the set of pairs xy such that x is preferred to y. This is a deep theorem, not very easy to prove. Okay? If you remove this assumption of continuity of the pre-order, no utility representation may exist. I'm going to give you a very easy example of a simple total ordering on Rn, which cannot admit any utility representation. As I mentioned yesterday, this is the lexicographical order. To make things simple, let us do it in R2. But the same argument, with no changes, works for every n greater than or equal to 2. So in R2, well, I consider R2, but it could be R plus 2, because as you are going to see, the argument is a matter of cardinality, and the cardinality of R is the same as the cardinality of R plus. Then consider two vectors, xy in R2, and we say that x is lexicographically greater than or equal to y if this means that either x1 is greater than y1, or they are equal and then the second component of x is greater than the second component of y. So we order vectors, and this is the same in Rn. I mean, to compare two vectors, if they are the same, they are the same. They are related in whatever order. Okay? But if they are not the same, we look at the first component, which is different. And then the one which is the largest different component is the largest vector according to the lexicographical order. Like words in a dictionary, we classify them according to the first letter. If the first letter is the same, we go to the second letter, and so on and so forth. So this is why lexico appears in this definition, in this terminology. Okay. Observe that this preorder is not continuous. So the Brecht's theorem does not apply. To give you an example, you have 1 over k, 0, lexicographically greater than 0, 1 for every k, because you just have to look at the first component. 1 over k is greater than 0. But let us take limits as k goes to 0. Then you get 0, 0. And here you keep 0, 1. And it's not true that this is lexicographically greater than or equal to 0, 1, because now you have to look at the second component, because the first components are the same. Okay, this means that the graph of the lexicographical order is not a closed set. The pair consisting of these two elements is in the graph, but their limit is not in the graph. So it is not closed. So we cannot apply the Brecht's theorem. So we don't know if there is a utility representation or not. We know that there is no continuous utility representation, because the Brecht's theorem says there is a continuous utility representation if and only if the graph is closed. The preorder is continuous. So no continuous utility representation can exist. But what about utility representations which are not continuous? In principle, they might exist, but they don't, as I'm going to prove. For any real number x, consider the pairs x0 and x1. Which one is greater lexicographically? The second one. The first components don't decide, but for the second component, it's clear that this relation holds. Then, assume there is a utility representation. We will see that it's impossible. Then we would have u of x0 strictly less than u of x1. Okay? Well, I said representation is with non-strict preferences and with non-strict inequality. But it's very easy to see that if this holds true, this also holds true. X is strictly preferred to y if and only if u of x is greater than or equal to u of y. Y, I mean, in this direction, if x is strictly preferred to y, first of all, x is preferred to y, so u of x is greater than or equal to u of y, but we cannot have u of x equal u of y, because this would mean that y would also be preferred to x, because u of y is greater than or equal to u of x, and this is impossible because we are assuming a strict preference. And the same in the opposite direction. If u of x is greater than u of y, first of all, we know that x is preferred to y, but there might be indifference in principle. But if there was indifference, then we would have u of x, I mean, if it was the case that x is indifferent to y, then u of x would be equal to u of y, which is a contradiction. Okay, so even though I define utility representation in this way, this is an immediate consequence. And this is what I am using here, that the inequality is strict. Then u of x0 and u of x1 are real numbers. They define an open interval. So we have an open interval of real numbers. And as you know, in every real interval, there are infinitely many rational numbers and irrational numbers. I just pick one, which I call qx, q sub x, because it depends on x. For every x, I make this construction, and I pick a rational number. So I have defined a function from the reals into the rationals, which to every x associates the corresponding qx, a rational number which is in the interval ux0, ux1. Okay? And let's see that this map is strictly increasing. Suppose x is less than y. Then qx is less than u of x1. Yes. Hmm? Yes. Yes, we choose one. We pick one. Yes, you randomly pick one. Corresponding to x. So in the interval u of x0, u of x1, there are infinitely many rationals, choose one. You don't agree? Well, this may be the axiom of choice, if you want. So we are accepting the axiom of choice. Okay? And so is this clear or not? Yeah. But now, notice that x is less than y. So, which vector is lexicographically larger, x1 or y0? y0. Look at the first component, which means that u of x1 is strictly less than u of y0. Okay? And remember that qx is between u of x0 and u of x1 for every x, in particular for y. So qi is between u of y0 and u of y1, which means that it is less than or equal to qi. This proves that this function is increasing. For y larger than x, qi is strictly larger than qx. It's strictly increasing. Then it is injective. Which is impossible. You cannot have an injective function from the reals, which has the continuum, the cardinality of the continuum, they are uncountable, into the rationals, which is a countable set. Okay? So no utility representation exists, even if this continues. Not at all. Is this clear? So everything I'm going to present does not apply to the lexicographical order, because there is no utility representation. But this is somehow a pathological case, and for this reason I told you yesterday that the lexicographical order is often mistreated, exhibited as a monster like I did today. Look at this monster that does not admit a utility representation. But there are other properties that compensate this pathological behavior. One of them is that in Rn, up to an isomorphism, the lexicographical order is the unique total order compatible with the vector space structure of Rn. So let me give you some details. I'm not going to prove it, but which one is the best for this? This one. Thank you. So consider a total ordering. The same can be done with preorderings, very similar. But let's consider order, a total order. So on top of that properties, we assume antisymmetry. There is no indifference. An element is only indifferent to itself, not to anybody else. Total order on Rn. I say that it is compatible with the vector space structure if the following two conditions hold. x greater or x preferred to y and x prime preferred to y prime imply x plus x prime preferred to y plus y prime. And x preferred to y and lambda positive or 0 imply lambda x preferred to lambda y. Okay, this is compatibility with the vector space structure. We can add two relations and we can multiply a relation with a non-negative number and the relation still holds. Okay? Then, this is a compatible total preorder if and only if there exists a non-singular square matrix of order n such that x preferred to y if and only if ax is greater than or equal to ay for every xy in the space. This matrix A, which is non-singular, defines an isomorphism, an automorphism of Rn. So, up to this A, we have the lexicographical order. So this is what I said. You have a total preorder on Rn which is compatible with the linear structure of the space, then it is the lexicographical order up to an isomorphism. I mean, you apply an isomorphism, and under this isomorphism, it is the lexicographical order. This is what this result is saying. This is exactly the opposite of saying that this is a monster. This is the only good compatible order. If you want preorder, you can, no, sorry, I said preorder, no, order. This is an order, sorry. If you want a preorder, you have to change here a square matrix by a general matrix, and then the same holds true. Okay? Which means that, I mean, up to an isomorphism, up to A, this means x greater than or equal to y lexicographically, and we know the meaning. But suppose A is singular, then the range is not the whole of Rn, and then let's say the range after another isomorphism is the space for which the last n minus k components are equal to 0. So this means that the preorder is given that by x1 xn preferred to y1 yn if and only if x1 xk, I only take the first k components, is lexicographically greater than or equal to y1 yk. And I don't care of the remaining components. This is why it is a preorder, because then we may have indifference between these two vectors. If the k first components are the same, but they are not the same vector if the remaining components don't coincide. Okay? So the unique order or preorder up to isomorphism. If you are not yet convinced of the nice properties of the lexicographical order, I will give you still another argument. So I'm compensating the insult we made of discovering a bad property of the lexicographical order. It's non-representability. So I'm compensating it with this, and still now with something else. We'll run the separation theorem for closed convex sets. An immediate consequence of the separation theorem is that a set in Rn is convex and closed if and only if C is an intersection of closed half spaces. C can be expressed as the intersection of a collection of closed half spaces. From right to left, there is nothing to prove, because if C is an intersection of closed half spaces, the intersection is closed, being an intersection of closed sets, and convex, being an intersection of convex sets, because half spaces are convex. So from right to left, we don't need anything. But from left to right, we need the separation theorem, because suppose C is convex and closed, and consider the intersection of all closed half spaces that contain C. Clearly, we have this inclusion, because C is contained in every element in the family. But we have equality, because suppose we have one point in the space which is not in C. Then we can separate it from C. Means there exists X star in Rn and K in R, such that X star X is less than or equal to K, or X star Y, no, X star X is less than or equal to K for every X in the set but this is less than or strictly less than x star x bar. Okay? The set is here and the point is not there. But this defines a half space, a closed half space. Call it H. This is a closed half space. Well, it's a real half space if this is different from 0. And of course, the separation is with a non-zero vector. It is a closed half space. And what we are saying here is that C is contained in H because every element in C satisfies the inequality that defines H. But we are saying here that x bar doesn't belong to H. So we have found a closed half space that contains C. So it is in this family, but does not contain x bar. So x bar is not in this intersection. So if x bar is not in C, is not in the intersection. This proves the opposite inclusion. So we have equality. So set is closed and convex if and only if it is an intersection of closed half spaces. But what if we remove convexity? Not convexity, we remove closeness. So can we have a similar equivalence as here? With C is convex, but not necessarily closed? Is there another class of sets which play the role of closed half spaces in that statement? And the reason, the answer is yes. C is convex if and only if C is an intersection of, there are many ways of expressing this statement. One is an intersection of so-called hemispaces. Actually, of hemispaces of a particular type. So what is a hemispace? It's a convex set whose complement is also convex. Closed half spaces are hemispaces because the complement is an open half space. Open half spaces are hemispaces. Okay? Because its complement is a closed half space which is convex. Are there any other hemispaces? Yes. For instance, in R2, consider an open half plane union an open or closed half line in its border, in its boundary. This is a convex set, this union. No matter if this point belongs to or doesn't belong to. And what is this complement? Another set of the same type. So it's also convex. Okay? And how can you describe hemispaces? Because half spaces we can describe very easily by linear inequalities. So how can you describe hemispaces? So H is a hemispace if and only if there exists a matrix m by n with m less than or equal to n. You can take A with rank equal to m, full row rank, if you want. And there exists a vector B in Rm such that X belongs to H. Let's call it a hemispace of type 1. Such that X belongs to H if and only if AX is lexicographically less than B. Okay, there exists B such that, I mean, in the same way these are represented by linear inequalities, well, they are also represented by linear inequalities, but defined by means of the lexicographical order. I said of type 1, of type 2 is with less than or equal to. I mean, H is a hemispace if and only if it is either a hemispace of type 1 or a hemispace of type 2. Okay, and then here you have the description of hemispaces of either type. In fact, for this theorem, you can consider just hemispaces of type 1 and with m equal n and A non-singular. It can be proved. In the same way, at this result, in the classical case, follows from the separation theorem, as we proved. This is an easy consequence of the following separation theorem. If X is not in C, X is in Rn but not in C, then this happens, or if and only if the if is evident, there exists a matrix A, let's say X bar, a matrix A n by n non-singular such that AX is lexicographically less than AX bar for every X in C. As I say, implication from right to left is evident, because if this holds for every X in C, X bar cannot be in C, because X bar does not satisfy this strict inequality. Okay, the interesting part is the separation part, showing that if X bar is not in C, then you can find a singular matrix that, please. The example I gave before? Okay. So suppose, for instance, that this is our half space, okay? Not including this point. So this is the set of points such that xy is less than, lexicographically less than 0. No. Instead of this, no, it was correct. So because which are the elements here? Those for which x is less than 0, plus those for which x equals 0, the first component coincides with the first component, but the second component, y, is less than 0. Okay? Is this clear? Then, so you can define a convexity in terms of the lexicographical order, because this is an equivalence. You can say C, a set C is convex if and only if it is an intersection of sets described in this way. And this is equivalent to the classical definition of convexity. So you see the very nice properties of the lexicographical order. The only ordering compatible with the vector space structure up to an isomorphism, and it defines convexity. Okay. Before continuing with this topic, I want to answer you for the third time your question about the function mod of x plus y. Okay, I already gave two answers. The first one was incomplete because we didn't make the computations. The second one was based on the composition rule. But yesterday, I liked that in the lecture of Dr. Laja, he presented a very nice and useful formula, and I want to use that formula to give you an easy solution to your problem, an alternative solution. Very easy, it will take very short time. So what Vivek did yesterday was to prove that if f is the maximum of a finite collection of functions each of them being convex. And if x bar is a point belonging to all the domains, he gave a formula for the subdifferential of f at x bar, which was, this is the convex hull. I don't remember if he used conv for convex hull or just CO. Conv is the notation used in Rockefeller's book, but in recent times CO became more popular. I don't remember what he used. CO, just CO. Okay, so it's the convex hull of the union over I in I of x bar of the subdifferential of fi of x bar, I of x bar being the set of I between 1 and k, for which the maximum is attained. This is called Valadier's formula. Valadier is a mathematician from the University of Montpellier in France. Montpellier was for some time the capital, world capital of convex analysis. Still is in a sense, but in the 80s already they created a weekly seminar, probably because Jean-Jacques Moreau was there. Moreau was a physicist, but who did very important work in convex analysis. There is Moreau-Rockefeller theorem, also in generalized convexity, Moreau. And then probably it was his school. Then there were two important people, Castaing, he was a Vietnamese but working in Vietnam, and Valadier, who proved this formula. And then the next generation was also very important. There was Hediatus, who unfortunately passed away a couple of years ago. There is Lionel Thibault, who is the editor-in-chief, or co-editor-in-chief, but he's the main editor-in-chief, I think, the one who is working more actively, of the Journal of Convex Analysis. So a very important place for convexity. Well, then, now we can use this to solve your problem. Because, so your function is f of xy equal absolute value of x plus y. And this is a maximum. This is the maximum of x plus y and minus x minus y. Then we can apply this formula at the points where x plus y is equal to 0. Because if x plus y is different from 0, we don't need this formula, because at those points the function is differentiable. So consider x bar y bar such that x bar plus y bar is 0. So what's the subdifferential of f at such point? according to this formula, is the convex hull of this union. But what is this union now? What is I of x bar y bar? Is the set of indices 1, 2, where the function coincides with its maximum. In this case, the maximum is 0, and both of them are 0. So I of x bar y bar is the whole index set, is 1, 2. So this means that it would be the convex hull of the subdifferential of f 1, and what is f1? X plus y, okay, which is 1, 1, because it's differentiable. Union, you can write it like this. Union, the subdifferential of the second function, which is the singleton of minus 1, 1. So it's the convex hull of these 2 points. The segment joining them. This we obtain by a different method. I could give you a third answer to your problem. There may be many, but there is another possible answer. Convex functions in Rn, we are always talking in Rn. In infinite dimensional spaces, things becomes very messy. There are many technical details, and one has to be extremely careful. This works in Hilbert, but not in Banach. This works in reflexive Banach, but not in Banach. This was in Asplund spaces, but not. Is a nightmare. But in Rn, we are very happy. Well, then in Rn, it is well known, it's proved in Rockefeller's book, and it's not hard to prove, that convex functions are locally Lipschitz. Okay? Then there is an old theorem, more or less 90 years old theorem by Rademacher, in the 1930s, who proved that locally Lipschitz functions are differentiable almost everywhere with respect to the Lebesgue measure. Hence, convex functions are differentiable everywhere in the sense of the Lebesgue measure, which means that, in particular, means that every point in the interior of the effective domain of a convex function is a limit of points at which the function is differentiable. Okay? Then collect all the gradients of these functions at the points where it is differentiable, and take the limit as the point goes to our point. It is possible because we know that the point is a limit of such points. Then the convex hull of all the limit, closed convex hull, of all the limit points of these gradients is the subdifferential. So in this case, we have this half line, x plus y equals 0, where the function fails to be differentiable. In the open half planes defined by this half line, we have differentiability. So at any point here is a limit of points around in either half plane, and on one side the gradient is 1, 1, and on the other side the gradient is minus 1, 1. Take the limit, are 1, 1 and minus 1, 1, and take their convex hull, and you get that. Okay, so there are many possible ways to approach your result. The most natural ways, in my opinion, are this one, with the maximum, with the Valadies formula, or the one involving the composition with a linear function. Okay, this explanation was motivated because yesterday I liked that Vivek gave this result, and I wanted to show you an application which is an answer to your question again. But let's go back to our topic now, which is consumer theory. One says that total preorder is convex when the following implication holds true. If I prefer x to y and lambda is between 0 and 1, then I prefer 1 minus lambda x plus lambda y is preferred to y. Okay? So if I prefer x to y, and I am with y, and I move in the direction towards x, because x is better for me, I am improving. This is quite natural assumption for preferences, as I just justified. But be careful. Using the same argument, you could impose something else which we will not do. To say that x is preferred to 1 minus lambda x plus lambda y. I mean, using the same argument I used here, if x is better than y for me, and if I move towards y, I am worsening, then I should prefer x. This is not true for most reasonable preferences. I will give you one example. So, consider there are two goods, bread and water. And I consider these two vectors, you have 1 kilo bread and no water in one commodity bundle. The other is no bread and 1 kilo water. Suppose you are in the desert, okay, and I meet you and I'm very generous and I offer you choose which one commodity bundle you prefer the water? Okay. Me too. Okay. But then a convex combination is preferred to 1, 0. This is reasonable, as I said, because I am moving in the direction of from the worst, 1, 0, which is just bread, I'm thirsty, I'm moving towards the good direction, which is including some water. But you wouldn't say, I wouldn't say at least, that I prefer 0, 1 to 1/2, 1/2. This I wouldn't say. Even though I like water, but I like eating from time to time. Okay? So this is a reasonable assumption. This is not. Do you agree? So this is the definition of convexity. For a total preorder on Rn. Oh, it is time, no? We started. Well, let me finish with the definition of a strictly convex. Is the same, but with the following modifications in the definition. Here you have to include x different from y. Here you have to replace closed interval with open interval. And here you have to write a strict preference instead of the non-strict one. Okay, so preorder is strictly convex is whenever you have x preferred to y and different from y. I'm not saying indifferent, I'm saying different. They may be indifferent. Between 0 and 1, then a convex combination is strictly preferred to y. We'll continue on after the break.